long would it really take to visit every planet in our solar system? Let's call it the ultimate space road trip. We'll make one itinerary, visiting all 8 planets without shortcuts. The total distance is about 39 AU. At 1/10 light speed, that's 583 days. At 1%, it's 16 years.
Imagine we have a spaceship. Not a sci-fi Millennium Falcon, but an actual spacecraft that could be built in our lifetime using technology we understand today. We can't visit every star, but we can visit every planet in our own solar system.
Think of it like a bucket list of planetary travel destinations. But here's the catch. Navigating through space means battling primal forces and pushing the limits of physics. This isn't a straight road trip. It's a complex dance with gravity, motion, and timing. The map isn't like any other. Before we go anywhere, we need a map. But our solar system map is unlike any you've used before. Our solar system map shows the sun at the center, with planets in elliptical orbits. But the distances are immense, from Mercury at 0.39 AU to Neptune at over 30 AU. This vast scale is what makes our map unique. Everything moves. Earth hurtles around the sun at more than 7,000 km/h, while every other planet moves at its own speed in its own orbit. When we launch toward Jupiter, we aren't aiming at where Jupiter is, we're aiming at where Jupiter will be when we arrive. It's like throwing a dart at a moving target from the back of a moving car, and you only get one shot. Miss, and you lose a decade of work and hundreds of millions of dollars. The reason? Fuel. You have exactly enough fuel to arrive in the most efficient way possible. One wrong turn, and you don't make it. It's like throwing a dart at a moving target from the back of a moving car, and you only get one shot. Miss, and you lose a decade of work and hundreds of millions of dollars. The reason? Fuel. You have exactly enough fuel to arrive in the most efficient way possible. One wrong turn, and you don't make it. The gravity problem. Before we can work with gravity, we must fight against it. Gravity is a force that pulls objects toward each other. To fight it, we use rockets, airplanes, and even a ball thrown upward. Rockets reach escape velocity to leave Earth's pull. Satellites stay in orbit because gravity provides the centripetal force. Escaping Earth. To reach space, we must break free of Earth's gravity. Our rocket burns through enough fuel to fill an Olympic-sized swimming pool every second of the 2-minute burn just to rise above the atmosphere. Once in orbit, we're moving at over 20,000 km/h faster than Earth itself, effectively outrunning gravity's pull. Orbital mechanics 10-1. Here's where it gets weird. From our perspective, we travel in a straight line, but Earth's gravity bends space, curving our path. This bending creates what we call space-time curvature. Objects follow this curved path, known as a geodesic. This is the principle behind orbital velocity and escape velocity. Speed up, and you travel further from Earth on a straighter curve. Slow down, and you risk crashing back to Earth on a tighter curve. To break free completely, we double our velocity to over 10,000 km/h. Now we're an object hurtling through the solar system at about 150,000 km/h relative to the Sun. Destination 1, Mercury. It takes 5 years to get there. Mercury is actually the hardest planet to reach. It's only 80 million kilometers away, but it orbits close to the Sun at 1,000 kilometers, and it's deep inside the Sun's gravity well. The challenge is to slow down enough to fall toward the Sun and control the fall to orbit Mercury, not crash. The gravity assist solution. Instead of burning impossible amounts of fuel, we use gravity assists, like the NASA Messenger probe, which took 6.5 years. The route. Fly past Venus, its gravity bends our path. Loop around the Sun. Second Venus flyby, closer this time. 3 flybys of Mercury, each bends our path closer to orbit. Final burn to enter Mercury's orbitum, about 5 years. Destination 2, Venus. A 5-month trip. Venus is our closest neighbor and shortest trip. But we're still falling toward the Sun, so we're moving too fast. Why Venus is easier. Larger gravity, nearly 3 times stronger than Mercury. Thick atmosphere, 100 times denser than Earth's. We can use aerodynamic drag to slow down. Combine these natural forces with a strategic engine burn, and we can orbit Venus in under 5 months. Destination 3, Mars, an 8-month journey. Now we fly away from the Sun for the first time, accelerating up the hill of gravity. This is the Hohmann transfer orbit. We wait for Mars and Earth to align, an opportunity that comes once every 2 years. Then, we launch at just the right speed. The problem, Mars moves slower than Earth, 86,000 km/h. There are no planets for gravity assists, no thick atmosphere, and weak gravity. We must burn fuel to slow down. This is why it takes 8 months. We could go faster, but we'd never slow down enough to orbit. Destination 4, Jupiter, in 3 years. Jupiter is 5 times further from the Sun than Earth. This is where things get interesting. Gravity assist to Jupiter. We use Venus's gravity to fling us outward toward Jupiter. 2 challenges. The asteroid belt. Mostly empty space. Rocks are spread so far apart you could fly through 100 times and never hit one. Jupiter's massive gravity, 2.5 pecs more massive than all other planets combined. The slowing down problem. Jupiter cruises at 47,000 km/h while we're traveling over 5x that speed. But Jupiter's powerful gravity can bend our path into orbit even at high speed. When NASA's Juno probe arrived in 2016, it burned its engine for 35 minutes straight just to slow down enough for orbital capture. Total time, 3 years. Destination 5, Saturn, 7 years. If we don't slow down at Jupiter, we can use its gravity as a slingshot to reach Saturn. Distance issue. Saturn is almost twice as far from the Sun as Jupiter. We spend years just coasting between the two gas giants. Why Saturn is easier? Saturn is at 1/3 of Jupiter's mass, meaning weaker gravity. Slowing down is much easier. Destination 6, Uranus, 13 to 15 years. We repeat the gravity hopping technique, using Jupiter and Saturn to fling us outward. For the M, the multiple planets slingshots, they must mark clubly. And then his grand tour line event won't happen until 2027 to 2052. But there's hope. A 2031 launch window could use Venus and Earth for gravity assists. Destination 7, Neptune, for ages 12 to 15. Neptune is 30 times further from the Sun than Earth, 6 times further than Jupiter. Sunlight barely registers here. Voyager 2 took 9 years using the rare planetary alignment. Without it, we're looking at 15 years maximum. Destination 8, Pluto, 20 years. Technically not a planet, depending on who you ask, but let's go anyway. The New Horizons problem. NASA's probe reached Pluto in 10 years, traveling at 83,000 km, while Pluto moves at 17,000 km/h. To actually stay at Pluto, we're looking at 20 years. Total journey time, about 64 years. Let's add it up. Mercury takes 5 years, Venus 5 months, Mars 8 months, Jupiter 3 years, Saturn 7 years, Uranus 13 to 15 years, Neptune 12 to 15 years, and Pluto 20 years. That adds up to about 64 years. Let's visualize this journey. From the Sun, we travel to each planet in order. The total time is about 64 years. Visiting every planet in our solar system is a lifetime commitment. You'd want to start young or strategically choose your favorite destination. But if you want to learn about every planet in detail, there's no better place to start than Mercury and the shocking discoveries NASA found there. Let's start with a look at the solar system.